Try that. Try that.
Yeah.
You forgot a semicolon there.
Vaginals are everywhere, most of the time we're unaware, but horses know we're leaking all the time. When looking in the fridge, when coughing does the bidding bridge, use vaginals for fun and for the prize, cause vaginals are with us all the time.
Only noise.
Yeah, on this blog post writes that as well.
Yeah. Maybe it doesn't work. Yeah.
You ready?
Yes.
British mathematician, Second World War.
Alan Turing.
German Chancellor.
Angela Merkel.
Yeah.
I have an idea. If it's my turn, I will say Manuel's girlfriend.
Let's skip that one. Okay.
Well, then it's our turn, right?
Yes.
Mm-hmm.
Famous Pokemon.
Pikachu.
Yes. A famous duck from a comic.
Donald Duck.
Manuel's girlfriend. Oh, yes.
No. That's definitely...
So, the name starts with CH, right?
No.
Yes. No. Yeah.
But this reminds me of something that we've been working on. Trying to deliberately access some information that you're not supposed to access.
Let's go through it systematically.
Mm-hmm.
So you want to directly leak kernel memories, similar to a Spectre attack?
Yeah. Mm-hmm.
And for that, you access the kernel address?
Yep. We dereference it here. See?
Shouldn't that trigger a fault?
It should. When we were working on the prefetch sidechannel attack some weeks ago, I came across another paper that did that just with normal memory access.
Mm-hmm. Yeah, and that should trigger a seg fault.
Well, people call it a seg fault. Actually, it's a page fault. It has nothing to do with segmentation today.
But the signal is called zigzag-v.
On Linux.
But in that paper that I mentioned, it was by Hundertart, there they broke KSLR and they used a signal handler to catch the zigzag-v.
You can do that?
Yeah, sure.
And apparently thousands of those per second. It's crazy.
So back to the topic. You deliberately access a kernel address.
Yes.
And then you catch that fall with a signal handler.
No. Yes. What?
No.
I thought you use a...
No, I have the access behind a branch prediction.
Oh, a misprediction.
Mm-hmm.
There, okay.
So we have our memory access and our theory here.
It's Anders Fogg's theory.
Yeah. So the theory is that the memory access is actually performed. But why has no one ever seen this before?
Because it vanishes. It's only there for a short time. We could call it transient.
Oh, so the instruction gets us the value from the kernel, but we cannot really leak it because the piece of code shuts down immediately.
Yes. Like with the speculation and the speculative window, there must be a time window where the value can be used.
Speculative window?
It could be speculative, but I'm now rewriting it to not use speculation anymore.
Okay. Sounds
okay,
good.
so then you use the same cache covered channel as for Spectre within this time window?
Exactly.
Okay.
Yeah. But then let's call it transient window. Transient. Mm-hmm. That's a nice term, yeah.
Because you suggested it.
When we were working on Spectre and Meltdown, we initially thought it's all speculation. But then we realized that they have some distinct properties, differences. So we discussed different terms that we could use to express that it is not just speculation, and that it doesn't really depend on speculative behavior. Nothing is speculative about a memory access to a kernel address that the user deliberately performs architecturally, memory access.
And then you called it transient?
Yeah, and transient basically includes both cases. It just means instructions or operations that are first executed during out-of-order execution, but are then undone and unrolled. So they only exist for a short amount of time, a short time window, transiently.
Ah, the transient execution window.
Yeah. And the CPU vendors, initially they also used speculative execution as a term, but now they also adopted the term transient execution because it's just more precise than speculative out of order.
Does it work?
Still only garbage.
But you two do realize that computers are actually largely deterministic machines.
What does noise even mean then? We have timing variations in there. The leaked bytes, all of this varies, and it doesn't leak the correct data. Maybe the attack doesn't work on all addresses.
What about the direct physical map? I mean, you have user memory in there.
Why would I want to leak user memory? I'm running a user-space program.
But memory of another user process. Just start at a random offset in the direct physical map. And and then in the part that is backed by RAM, there you should see something.
What do you do in the transient window?
Look here. So I encode the value I want to leak in the cache, exactly like in the blog post of Anders Fogh. So I want the value at the secret address. I take the lowest 8 bits and I shift them by 12. And then I access the array mem at this location.
Ah, so you use this character that you read there as an index for the array.
Exactly.
That makes sense, but why do you shift it by 12?
Because that was in the blog post.
Maybe to avoid the prefetcher. Because the prefetcher would start prefetching if you access multiple locations within the same 4 kilobyte page. And with shift by 12, that's a multiplication by 4 kilobytes, you shift it to the next page.
Ah, yes, that makes sense.
Yeah.
And down here, I use the flush and reload loop to recover the data from the cache.
Okay.
And then I just print it here.
Okay, so you first encode the secret 8 bits, which could be anything, any value from 0 to 255, into an array access, and then you check it with flush and reload, whether
here
or which array index was accessed.
Exactly.
That's pretty clever. Nice trick.
Thanks. That's from the blog post.
It's probably not the fastest option though. Think about it. 256 times flush and reload will be slower than transmitting it bitwise, where you only need 1 or 2 flush and reloads per bit, not 8.
Yeah, but let's first check if it works before we start optimizing, right?
Only noise.
In a completely deterministic machine?
A wise person once told me there is no noise. Noise is just someone else's data.
A wise person.
Also, for this part, I would like to write it along the lines of how Moritz, Michael, and I actually saw the first leakage with our first Meltdown proof of concepts. Wait, what was that? That could be from some, I don't know, MIME encoding or something.
No, that's nothing.
What about this?
Oh.
Looks like a URL or something.
It is.
I think that's some ad
and
server.
This is like HTML tags.
Have you opened some website with ads? Or do you have an ad blocker running and maybe it has this URL on its list?
It could be an ad blocker.
What are we going to do? I mean, this can leak everything. All the system memory, like from the direct physical map, this could leak my passwords or my browsing history, anything. What are we going to do with this? This is like a complete meltdown of all security boundaries. Wow. But the blog post, so this is pretty much what he did. Maybe we should get in touch with him and ask him like what the status of this is and whether he knows anything about it.
And you think Anders would respond to this email?
Actually, I asked him, but long story short, anyway, I asked Thomas Prescher, with whom I've worked on the Meltdown paper, and we'll just have a call with him instead.
Ah, I got a mail.
From Thomas.
Oh.
Yeah, he would be available for a call. Now. Do you have time?
Yeah.
Sure. Yeah. Hi.
Hi. So nice to meet you.
Yeah, so what did you want to discuss?
So we tried out the idea of Anders Fogg's blog post.
And?
It works. You can read kernel data.
Really? What machine is that?
It's an i7-8550U.
It should not work. It has patches already.
What?
Against Meltdown?
Meltdown?
Didn't you come up with that name?
Yeah, but not in the show.
That was published in 2018. Jan Horn actually was the first who discovered it and reported it in 2017.
So this is not new?
No. Can you check proc CPU info? What does it say about bugs?
Nothing.
Nothing? Are updates disabled on that machine? Maybe?
I'm running some old kernel version here. On newer versions, my Wi-Fi stopped working.
And microcode updates?
Disabled them too, yeah, because same problem.
Okay, so you're telling me that you're running an insecure system on the security level from 2017.
But this leakage looks quite scary. We should report this to Intel.
Well, try this with all microcodes and all kernel updates installed. If it still works, you can report it to Intel. But if it's what you described, then I think it's Meltdown and known and mitigated since early 2018. In both hardware and software.
Oh, thank you so much for the call, Thomas. Sorry for wasting your time.
All good. I would be curious if you find something new in this area of microarchitectural research. Have a nice evening, guys.
Bye. Then he said it already exists, and it's basically, it has the name Meltdown. It was published in early 2018, and it was, published when the embargo broke on Meltdown and Spectre.
Yeah, now I remember. It was published along with Spectre. It was a really long embargo.
So that was after the initial reports by Jan Horn then?
Yeah, I think it was summer 2017. And then multiple other groups also discovered Spectre and Meltdown, and they coordinated on some research papers, I think.
How do you mitigate Meltdown?
Wait.
Sure.
Well, there are multiple stages in this attack, very much like in Spectre. You could see it like 6 phases.
Oh, yeah. In Spectre, you start with some kind of preparation phase where you mistrain the branch predictor.
Yeah, in Meltdown, you might also do something before, like somehow assist Meltdown by pulling things into the cache.
Wait, in the cache?
Yeah, Meltdown leaks from the L1 cache.
No, we also leaked data that was not in the L1 cache.
No, yeah, you might have implicitly pulled it into the L1 cache.
Oh, okay. So...
Well, then the second phase is the trigger instruction.
So in Spectre, this would be the branch instruction, and in Meltdown, the access to kernel memory?
Exactly, yeah. And then we have phase 3, transiently accessing the secret.
Okay. And in this phase 3 and phase 2, in Meltdown, this is a single instruction. In Spectre, this is 2 separate instructions then, the branch and the access.
Yes.
Phase 4 is quite logical to me. So phase 4 is basically just we transmit the secret via some covert channel.
Yeah, and then phase 5.
Recovering the secret?
No, actually that's phase 6.
Okay.
The covert channel receiver.
Okay.
Phase 5, you have the cleanup or fix-up.
Okay. And in Spectre, this would be reverting the misspeculation?
And in Meltdown, much more. You get a fault, you have to revert all out-of-order executed instructions from that point on, and instead trigger a fault on that instruction.
Oh, so the operating system receives that fault.
Exactly. And then it sends the signal to the user space. And keep in mind for phase 5, it's not perfect. The cache state remains, for instance, and is not cleaned up.
But why are these phases important then for the mitigation?
Well, you can focus on any of these phases.
Like preventing the transmission, for instance? By preventing flush and reload.
Yeah,
we could do that.
Then you got prime+probe.
Oh. And yeah, probably also many other channels as well. So yeah.
Yeah, exactly.
Okay, that's phase 4 and 6 are also not very interesting for mitigation then, right?
Also, phase 1, you often don't need it at all, as mispredictions could also occur incidentally due to system activity.
Yeah. What do we have left? Phase 5? Can we mitigate it in phase 5 then?
Well, there are some theoretical ideas on how to revert microarchitectural state, but theoretical.
What do we have left? Phase 2? Phase 2 could be an opportunity to
you want to prevent that misspeculations occur or faults can be triggered? Well, have fun, I guess. Then you also have to eliminate the counterparts, like useful speculation and out-of-order execution.
So, but then phase 3 is the only remaining one accessing the secret.
Exactly, and there are many proposals on how to do that for spectra, and the meltdown mitigations also act here.
Oh, so everything in the attack would still be the same, but instead of actual kernel data, would you then read something else?
Well, for instance, zeros, or maybe nothing, because the CPU stalls instead.
Okay. Thomas also mentioned that Meltdown can be mitigated directly in software. Do you know anything about that?
Well, I checked the Meltdown paper again, and it says the Kaiser or KPTI mechanism helps against it.
Okay, I know that one. From the prefetch attacks that we mounted some weeks ago, the idea was to not trust the user accessible bit in the page tables anymore, and instead just unmap those pages, those kernel pages.
Yeah, and that makes sense. The hardware cannot transiently access the secret if there is nothing, if the address translates to nothing.
That makes sense, yeah.
So the hardware mitigations instead make sure that either only zeros are returned or they stall in these cases.
But only on newer CPUs, right?
Yeah, exactly. Yeah. And non-Intel CPUs. There were a few others affected. And newer CPUs don't have that meltdown type behavior anymore.
Okay.
So keep it in small circuits too.
Yeah, of course.
Thanks.
But quite funny that I know her.
Yeah, actually is. What are you guys up to?
What? Yeah, I guess enough work for today. We discovered a new microarchitectural attack.
Another side channel?
Not really. It's not a side channel. We deliberately access kernel memory.
All right.
So you leak data, not metadata.
Yeah, that's right.
Yeah, we leak the data from the transient domain. And then we can use any cache cover channel to get it out.
That sounds like maybe you're getting famous soon.
No.
What?
Let me guess, somebody else discovered it already.
Well, then I guess you gotta keep searching, right?